you can see my screen.
It is visible.
Visible. Okay, thank you. So we will just go through the induction heating and the basics of induction heating. So induction heating is almost just like a hot plate you can see without gas. Hot plates, cooking hot plates. So it is almost like that. As you can see in the screen, I would say a conductor will be placed, which would be a workpiece, and around that there will be a copper coil. And then once you supply current to the coil, it will generate a magnetic field around the coil, and that magnetic field will interact with the workpiece, and then it will generate the eddy currents within the workpiece, and then it will start a self-heating within the workpiece. They both they don't have an interaction with each other. There will be an air gap between the coil and the workpiece. So it is faster. In this way, it is faster, better, cheaper, and clean. In any other heating equipments, you need oil or hot air, and they need always maintenance. In this case, we don't need any maintenance. The maintenance will be very, very, very minimal. So I will just run a video for you for a better understanding. Hope you can see my screen. Can you see the video?
In the video, we have not seen.
Okay, okay, just hold on then. Okay. Now you can see the screen.
Yeah.
So what is induction heating? Well, induction heating is a flame-free type. How does it work? Well, there are a number of ways to explain that. So here I have a handheld transformer fitted to quite a smart piston wheel. I'm going to use this very smart way, turn the power trigger, and fitted here is a single turn coil encircling, and we're going to run a high frequency current through this coil. In fact, this system automatically matches to the coil and the part heated. So in this case, we'll be around 20 kilograms of fluid. If I take a metal part, any metal, material actually, place it inside the coil with the run through, so we get a magnetic field, currents are induced into the surface of the part. So here we go. As you can see, I can put in heat exactly where I need it. I'm not getting hot, this stays cold, and it's very efficient. In fact, with our equipment, it's carbon steel, solid bar. With our equipment, we have low voltage on the coil. If you did happen to touch the coil, quite safe. How is this possible? The answer is surprisingly simple. Induction exploits the laws of electromagnetism in order to produce heat directly in the workpiece. The workpiece is placed in the coil, where this field induces a current in the workpiece, which generates heat in the workpiece. The coil, which is water-cooled and cool to touch, is placed around or adjacent to the workpiece. It does not touch the workpiece, and heat is only generated by the induced current flowing in the workpiece. Correctly designed, made, and maintained coil is crucial to the outcome of any induction heating operation. After all, it is the component that actually delivers heat to the workpiece. EFD Induction has years of experience designing and supplying custom.
Okay. I hope you were able to understand.
Yeah.
So that is basically the induction heating. We can heat the part wherever we want, to whatever temperature you want and precisely. Not like in any other heating mechanism where we use fuels and hot airs, it is very difficult to control the heat onto the specific location of the part. So in this way, even furnaces, you put whole part into the heat as a batches. So basically all this heating is mainly for heat treatment of the materials to make it much stronger. Okay, so this is the flame free, and which we use alternating current, and we will place the workpiece within the magnetic field so that it will induce the eddy currents which can generate heat within the part. So the materials which we can heat through induction heating are copper, steel, brass, aluminum, cobalt, but we don't have experience in all these because but the industries which we deal also depends on, they don't use all these materials. So our business is totally 80% concentrated, 75 to 80% is for automobile, and the rest 20% we will deal with other industries. Basically, induction heating is also a basic concept from transformer theory. As you can see, we have a primary coil and a secondary coil. In our case, the secondary coil will become the workpiece itself. So when you supply voltage to the primary coil, it will induce the magnetic field around it, and then that magnetic field, when interacts with the workpiece, will induce the eddy currents. With that, it will heat up. Here also the core will be heat up because of the magnetic field that generates from the primary coil. So induction heating has in fact developed from the transformer theory. And as I was saying that we deal about 80% mainly from the automotive components, from engine, crankshafts, body, doors and hoods, transmission, mainly shafts and clutches, other parts, suspension systems, and steering rods. We do a lot. Drive lines also we do a lot. CV joints like constant velocity joints and drive shafts. We do a lot of these components, and we deliver machines to the automotive industry directly so that they can do the heat treatments for their parts. That is the main thing. So we develop machines around this technology of heating around the induction heating. So that is the main thing. And then, as I said, 80% is automotive and 20% goes to renewable energy, aviation, metal foundry, cable and wire, shipbuilding. Shipbuilding is also a little more nowadays, but not in India, in Europe. And domestic appliances, optical fiber, very less, and others are also quite less. Tube and pipe, we are very much there. That's it. And what else? What kind of heat treatment we do? Hardening, tempering, brazing, bonding, welding and normalizing, shrink fittings, preheating, post-heating, forging, melting. Melting is quite less. And then for shipbuilding, we do some. So there will be a bending. We will remove the bends on the decks by induction heating. So these are all the virtual applications that we do for all the industries that we serve. Okay. So let's come back to the basics. We will discuss about the efficiencies and different parameters that affect the heating of the component or the workpiece that we would like to heat. So basically the heat rates and efficiency depends on the specific heat of the material, resistivity of the metals, and magnetic permeability. So if the specific heat is too high, then as you can see here in the chart, aluminum, steel, they have different specific heat capacities. So at different temperatures, we have different specific heat capacities and it will rise. So once it starts increasing the specific heat capacity with the temperature, it will be more, it requires more energy to heat the material. So I need more power to raise the temperature of the bar. If I want to raise by 1 degree, I need more energy, because it can take more energy if it has more specific heat content. So based on that, we will calculate the power requirements and all that, because then I need to design my cooling also. As you can see in the copper, it is a hollow tube. The coil is a hollow copper tube, which I need to cool down also all the time. So water flows inside the coil always whenever there is a heating cycle. So that's how we have to calculate the energies required for the heating, so that I need to cool it back the coil. So these are all interrelated. So, and the resistivity of the different materials. So steel, as you increase the temperature, steel exhibits increase in resistivity 10 times larger than when at room temperature. And when compared with the copper, steel have 10 times higher resistance than copper. So very difficult to heat, and it needs more energy. Okay. And of course, it will take little more energy when compared to any furnace and all that, because we virtually did experiments and calculated the power required for both furnace heating as well as induction heating. And there is one more technology called tunnel heating. So even if there is a 10% rise in the power requirement, but overall maintenance and accuracy levels will be much higher in the case of induction heating. And magnetic permeability, as I said, the coil will develop the magnetic field. That magnetic field will develop the induce eddy currents within the workpiece. So when we have high magnetic permeability, it is very easy to heat up the workpiece. So that means it needs less energy requirements for those materials which is having high magnetic permeability. So of course here it is in certain cases we just it is not just because of eddy currents. There is also one more concept called hysteresis losses, because of which also it generates heats within the component. That also depends on the temperature. At a certain point of time, materials don't behave as magnetic materials. That we can change. That temperature can be changed within the material using frequencies and all that. And once I know what energy I require to heat the material to the required temperature. Now the customer wants the depth of heat that it should go. If I take a bar of 10 mm, he says the heat should penetrate up to 2 mm. That means when I penetrate heat means I am changing the hardness of the material basically. Okay, then he says at 2 mm depth, the hardness should rise to this point. Some 500 HV or 600 HV depending upon their requirement. Now, how do I define my depth? How do I make sure that I reach the required depth of 2 mm out of a 10 mm bar? So we call it as a skin effect, or sometimes a few companies call it as a reference depth. So it depends on mainly, of course, the properties of the material, and well also the given frequency of the current. So we can so as you can see, the difference depth is dependent upon the resistivity of the conductor, frequency, and the permeability of the material, and angular frequency of the current. So how they impact the depth of the heating. So now we will see the impacts of all these parameters on the depth. So when do you say that one way of achieving is when I measure the hardness change within the material, I can say, okay, I have achieved the required depth. Even before that, can we say that this is the maximum depth it can reach? So for that we need to have this thing specification. So the current density which develops because of the magnetic field on the material should fall below the actual. It should fall below certain amount when compared to the surface of the material. Okay, surface of the conductor Js. So it should fall above about 0.37. Then we can say that is the maximum depth at a particular frequency for a particular material it can achieve. Beyond that, even if even the heat penetrates, there will not be any change in the hardness of the material. It will not change the properties of the material. So that's how we specify. So that's why you can see the graph. They compare. You can see how the frequency change can change the depth. For example, if you take for aluminum, so at 1 kilohertz we can achieve up to above 1 mm depth. If you want more, then we have to reduce the frequency. Once you reduce the frequency, then we can attain more depths. For a 10 mm, if you want to, we generally go for 2 mm max. Yes, we have went up to 4 to beyond 4. We call it as really higher depths, where we go for higher, lower frequencies. So yes, we went up to 5 mm, where we use very low frequencies to make the heat to penetrate into the material. Otherwise, it can, with high frequencies, you can never reach the penetration depths very high. So as I said, for poor conductors, we can achieve higher depths. For non-magnetic materials, we can achieve higher depths. And for low frequencies, we can achieve higher depths comparatively for good conductors, highly magnetic materials, and high frequencies. Okay, if they are poor conductors, then only the resistance will be more, and then the heat can penetrate further. The heat will develop within the material and can penetrate into and stays in the material and cannot penetrate further more into the material. So that's how if you want higher depths, then it should be a poor conductor and less magnetic, and we should apply low frequencies. That is the overview on the skin depth. Any questions?
Vijay, you will have the question at the last.
Okay, fine. Thanks. Okay. Yes. As you can see, skin depth also can vary with the temperature of the material. If you take a steel, ferritic steel, at 20 degrees, we can achieve close to 0.9 mm. And at the same material, at the same temperature, if you change the frequency, if you change the frequency, then we can reach very lower depths. Again, if you go beyond this Curie temperature, then we have higher depths of 2 mm when 100 kilohertz, and if you increase the frequency, then you will not achieve higher depths. It's only 0.9 mm. See, at Curie temperature, after Curie temperature, even if you increase the frequency or temperature, the depth of penetration change will be very minimal. So everything whatever I have to do before Curie temperature to attain higher penetration depths for a particular temperature. Beyond that, whatever the temperature and frequency, the change will be very, very minimal. That's what he's saying. It loses its magnetic properties completely. It ceases to be a non-magnetic material. Magnetic material. So non-magnetic materials may vary by a factor of 2 or 3 after the Curie temperature. Magnetic steels, that means below the Curie temperature, it can vary by a factor of 20. So whatever we have to do it before the Curie point of that particular material. And this is a reference depth for various material. This is only for bars, and we generally have different shapes. When you take yes, for steering rods and all energy transmissions, we have shafts. All these are bars, But when we go to hubs, there will be circular components which will be different, which will be little, the graphs will be little different, but they have done this only for the bars exclusively, but at least we can get a feel out of it. As the frequency increases, the reference steps are going for different materials, and you can see for room temperature, and there are certain materials which are already at higher temperatures. So as I said, even it is also an advantage and is also a requirement. As you go close to the center of the component, if at 10 mm, as you go into the center of the component, there will be no heat cannot penetrate, and it is also a requirement that the material should be soft in the center. So it gives a cushion to the hardened material which is outside. If you heat up the material through and through, it will give a crack. So this is an advantage from the induction heating where we don't get in others. If you put it in a heat chamber, then it will modify the whole component behavior, or it will harden the whole component through and through, which is not a requirement in certain components. Okay. So as I said, we have a reference depth beyond which we cannot penetrate into the material, and the current density also will fall beyond certain point where there will not be any change in the hardness of the material. That means the material will be soft, only soft even after that point, even heat penetrates. So at that point we call the frequencies as critical frequencies, because then we need to compare with the efficiencies again. If you look at the big picture, how do these critical frequencies affect my efficiencies? So what is the critical frequency for a particular diameter component? You can see for different materials, you can see steel at 500 degrees centigrade. As the diameter increases, the critical frequencies are going down. As we discussed earlier, it is going down. And you can see reference that I said it earlier, and I am just putting in a picture again. This is the test coil, and this is a circular piece, and with we will have a high frequency. If you have a low penetration depth, if you want to have a low penetration depth, then you have to use high frequency, high conductive, high permeability. So if you have a depth of more, then we should use low frequency, low conductive, and low permeability materials. So at the standard depth of penetration, the surface, when compared to the current density at the surface, it will fall by 37%. So we call it as critical frequencies. So when we start a job, we will look into these graphs, and we will try to find the relative practical frequencies for our materials. Okay. Generally, how the current distribution would be. Again, I showed the depths in a cut section. So if it is the A is the thickness of the workpiece, and D is the depth for the penetration depth. So in this depth, the hardness will be higher than the core, which is softer than the D. Okay, there is always a criteria. We need to look into this, very important. So as you can see, how do I explain? Okay, this ratio of A by D should always be 4. Oh, I would say minimum 4. It can be higher than that. It should not be a problem. So that we will have an equal current distribution across the component. Otherwise, you will have a non-uniform heating, because the interactions with the magnetic field will not be uniform, and also it is not efficient sometimes. In fact, it is not efficient, and sometimes it will be non-uniform. Yes. You can see when you take this edge to edge, 0 to 0, if you take A from this point to this point, this corresponds to 0 to 0. Okay. At the surface, whatever the applying magnetic field, corresponding current density will fall, and then we will have an efficiency close to 1. And then slowly it drops down as you go to the core. That means heat is not transmitting properly to the core. And then this point is this point in the middle of the component, and then drops down back to the, then again increases back to the this one. Of course, this we can achieve only when we rotate the component, as you have seen in the video. We must rotate the component to achieve the uniform current distribution on the component. Otherwise, we cannot achieve this. But of course, there is also new technology which we tried, wherein which we increased the residence time in the coil without rotating the component, so that we achieved these kind of graphs even without the rotation of the component. But the coil is little lengthier than the normal ones. Even not little, it is much lengthier than the other components. So even the current distribution falls to 0.8 in this case, and even drops further to 0.4. This can also create non-uniform heating within the component. So then my D will vary here and here. So we need to be really careful, and we should make sure that we start with A by D equals to 4. And this is the heat distribution along the same thing. My heat distribution is really uniform, reaches to 100% here. As I go down, when I reach to the 0 point, that means in the middle of the component, and then again it starts increasing. But it starts at 0.6. So best surface heat distribution occurs when A by D is equal to 0 and is above the Curie temperature. Austenization means it is a change, the hardness changes basically. Okay, I said about the critical frequencies. Okay, when we are at the critical frequencies, it is expected to be the relative efficiency to be 1. As we go down, that means when we change A by D ratio below 4, then this is how it falls. It falls very drastically, the relative efficiencies. That means it will not interact with the magnetic fields properly. But beyond the critical frequencies also, there is a very less probability that it can raise the, it can penetrate more. Beyond that, it can, so with that 100% of it, that is the maximum depth it can penetrate. Beyond that, even if you supply more energy, the penetration will be very, very minimal. Which is not the case in if you furnace heating, or if you keep 1 hour or 2 hour, 1 hour more, then it will penetrate more. So that is all about the induction heating. Of course, this is also a new area for me since I joined in 2009. Yes, 2009 with the EFT. But our main concern is we built machines around induction heating. We have to supply cooling coil, cooling water around the coils and the workpieces. We have to cool them immediately once the heating starts. Otherwise, there will be different properties. In the hardness, drop will change. So with we need to cool this electronics control panels, because it's supplied at very high frequency. So we need to cool all the electrical and electronic components within the power source. So that is the thermal part we are taking care of course, along with the machine building, structural machine building. That is what we are doing at India. Any queries on this?
You will talk to the reliability around now, or
Yes, I will talk reliability also.
Just you complete.
Yeah, okay. So reliability is also one thing which is close to my heart, which I think is very important for any industry. At least to my understanding, wherever I have worked, I saw the impact of reliability whenever I apply, whether the company needs it or not. But when I look into the reliability aspects, it really improved my design and my thought process, at least for sure, personally. So basically, reliability is defined as the probability that a product or a system or service will perform its intended function adequately. Intended function, that is more important. What it is meant for, adequately for a specific period of time, which is more important, or will operate in a, and moreover, a specific period and specific environment without failure. And at what conditions it has to work should be very clear. Otherwise, it will be a disaster for you. People start designing things by not knowing specifically the environmental conditions and as well as the specific time period that it is supposed to function. This is very critical for reliability, and defining these two parameters is also a little difficult. Sometimes customer gives, and sometimes we need to question them, and so that we can write the conditions for ourselves. Otherwise, certain times the environment is hidden. Until unless we talk more with the customer, we don't get these environmental conditions. It is very difficult. Trust me, these environmental conditions will sometimes kill your product at the end of the day. And Bosch has a lot of experience on this. And then people often ask about the difference between reliability and quality. Just to clarify the team and the participants also, reliability has sometimes been classified as how quality changes over time. As I said, time is very important. You see, quality, does the object perform its intended function? If so, how well does it perform its intended function? Suppose my engine is working at 80% efficiency. Fine, that is quality. But this 80 with 80% efficiency, how long it works? For 2 years, 3 years, or 5 years? I'm able to supply with my coil 180 degrees at a frequency of 200 kilohertz. Fine. But how long? If I run for 24 hours a day, will it work for 1 year or will it work for 22 years? So that is the difference between a quality and a reliability. And we, as I said, there is also one, since we talk about quality, there is also validation and verification. I'm saying the engine is 80% efficient. So that is called verification. And validation also means when I do testing the engine at 80% for 2 years and there is no problems, then I validated the engine for 2 years at 80% efficiency. So there is also a difference between validation and verification, like reliability and quality. These are very important in the reliability world. So for example, a vehicle gives 15 kilometers per hour with a great safety is called quality, but the same vehicle gives 15 kilometers per hour for 10 years with the same level of safety, it is called reliable. So when I say the pen is reliable or some product is reliable, the TV is reliable, that means I am talking about certain time. Without time, we cannot call it as reliable. It is just only a quality. So I will talk about a little bit on, we need to know when we are going to reliability, we need to go what is a bathtub curve, useful life, stress, load profiling, strength and target failure and testing to know the reliability of a product or service. As I said earlier, we need to know this. So basically bathtub curve, it was proposed long back for mainly electronic components. It was started with electronic components. So any component or any product or any service will have a initial failures. We call it as infant failures, and then after that it will have a constant failure rate. Then again it will have an increased failure rate because of wear and tear. So the time period within which where we have constant failure rate is what we are going to know by reliability engineering. This is where I will give my warranties and guarantees within this period. Okay. And after that, wear and tear will come. Before that, there is some infant failures. Oh, I can say some design or even certain manufacturing mm, uh, due to some manufacturing defects also, we can say that there will be failures during the period during infant failures. So basically, this curve we cannot avoid for any product. Either we have to reduce the time period for the infant failures and increase the time for the useful life, which we call it as where we have a constant failure rate. We cannot avoid failure, but we will have a constant failure rate. So we will always target what is my failure rate in my product? What is the probability of, as you said, probability of failure when you talk about the definition of reliability. So anyhow, after that, for every product, after wear and tear, it will start, the failure rate will increase, okay? So even this helps us to improve preventive maintenance and to stock up this thing, components which are required for that product, and it helps for many things. Time to market, everything. It can control many things. So certain times we need to do experiments to find this, and also we need to have a constant feedback from the market also, because we don't know infant failures until unless it goes to the market. And we can even in wear and tear also we can catch certain wear and tear in the labs itself, but still there should be always a constant feedback from the market to draw these curves. And it takes time to draw these curves for the products. But once we have these curves, it is very easy to play with the product and designs. Okay. So most of the products follow bathtub curve, and infant motor failure is high but rapidly decreasing as defective products are identified and discarded because of handling, as I said, installation error and manufacturing defects. And handling also can create infant mortality failures. Useful life failure rate is low and constant. End of life failure rate increases with the time because of aging and wear and tear. So the designer has to design for the useful life. What is my useful life? That's what we discussed in the definition of the reliability. For what specific period? 5 years or 6 years? Or 15 years. For automotive parts, generally they target for 10 to 15 years. So we will go deep into the useful life. So when you take a useful life of any component or subsystem or a system or a product, we call it as, even in the reliability world, even if it is a product, for the time being, they always call it as a design element. Design element or product experiences stress during the useful life. What happens? Why the product goes through, after a certain period of time, we will have wear and tear. So that means the product has experienced something. What it has experienced? It has experienced stress. Okay. Of course, it has experienced stress. Then what about its strength? It has its own strengths to combat the stress. Is it more or less? So when it fails, then the design element fails. Sorry, when the design element fails, when stress is higher than the strength. Okay. So we will slowly see where the stress comes from. Okay. But Are there any design options? As you can see in the graph, see this is the stress onto the component or any product, and this is the strength of the component or the product. So they will interact. This is the probable density function PDF for both stress and strength. So this is the region of failure where we can see at this point of time, when you take this point, the stress is low and the strength is low and the stress is very high. So it is intended to fail. So we try to avoid the product to run in these regions of failure. Okay, that is the main concept of reliability. Now we need to design the system in such a way that the working conditions should not fall in the region of failure. We will avoid that. So what are the other design options we have to do that? So either I have to decrease the strength. That means when I say that my product has to work from -40 to +100 degrees centigrade, no, it is not possible. The material can only withstand from 0 to 40 degrees. Okay. Now that's how I am reducing the stress on the component or the material slowly. So in the same way, I'm increasing the strength. Now, since I will know my working conditions, I cannot change. So it should be from -40 to +100. So then I will take another material to see that it can work within this range. Any material that works within the range. So that means I'm increasing the strength. I'm just giving an example. In the design also, we need to bring these aspects. Let us put 2 screws rather than 4 screws, like that. So we need to look into the what kind of stress. Based on that, we need to take a call. Corresponding strength, we need to increase, decrease, or decrease the scatter. So once you decrease the scatter, you see, if you decrease this scatter further down here, and then I will have a less region of failure, as it was showing here. I am reducing the scatter so that we can increase the strength. No, we can increase the region of decrease the region of failure. And the last option is decrease the scatter of the strength. So then we decrease the scatter of the strength itself. You bring it down to here. So the region of failure will also be very less. Okay, these are all the 4 possible options any designer should think when there is a situation of stress having higher than the strength. Okay, which prompts the design element to fail. Okay, then we will see what is the stress, what kind of stresses we have. Okay. Generally, stress can be estimated from formulas and numerical correlations and simulations. Basically, when you do ANSYS or any other structural simulations, you will get to know what kind of stress the particular component because of the loading. We can see it clearly, but we don't know the strength. Strength can be only estimated from the testing. Okay, there is no tool that can tell the strength of the material. All the softwares uses the data from the testing, and they will put that data into the software about the strength of the materials. Okay. So basically, stress is an end effect from a load. So stress is an end effect. It is a product of load. So for example, contraction and expansion of certain materials due to temperature. So temperature is the load here. And the stress is called it as contraction and expansion of the material. So if you want to know the stress, you want to know the loads first. So so we need to know the loads to understand the stresses. So then how do we know the loads? Loads, certain loads you will get from the customer, And certain loads, we need to really talk to the customer and identify the loads. I will tell you for certain examples in the later part of the discussion. But finally, at the end of the day, these loads will define the aging process. Okay, once you have a load, stress will create the aging process. And finally, the life of the product. This is the life cycle of any product based on the stress and strength. If it is stress is more, it will fail very fast. If it has an adequate strength, it will work for the useful life. Then I would like to know the load. So load can be different. You see, it is a temperature load, or it could be a mechanical load, or it should be a chemical load. It can be anything. But I should define it properly. And again, at the same time, we need to know the time for, as I said, it can withstand probably, if I say at 20 degrees, the material can withstand up to 1000 hours. And at 500 degrees, it can only withstand for 10 hours. So again, even the loading also, I should be able to tell the time for how long it will experience. See, as you can see the graph, if you see the temperature, at certain point of time, it is at probably roughly at 20 degrees, and then constantly, and then it will increase. Then it will go to 100 for a short time, and then it will come back, and then it will again operate at the room temperature. You can see most of the automobile parts in the engine, this kind of profiles. As far as my experience is concerned. So we need to really understand the load profile, and then we need to turn those load profile into stresses. Then only you can able to really tell the strength of the, what is the required strength for the material. Otherwise, it is very difficult if you don't understand the loads. And these are also critical for testing. So whether it can withstand the load profile or not, we will tell the by doing the testing. Try to cover maximum use cases using single load profile. Okay. Maybe Ashok Leyland has given this load profile, and Tata has given some other load profile. GM has given other load profile. There will be different load profiles. Let us try to take one load profile which can cover at least 60 to 70% other load cases. Once I cover 60 to 7%, then I will design accordingly to that, so that I can cover my 60 to 70% of customers. Then again, after that, the rest 30% are special cases where I will charge more for my customer. And even sales will ask for us, is it falls within the 70% or 30%, so that it will impact the costing for the end product. To that extent, the load profiles helps. Okay, and a little bit on the strength. Steel has a strength ratio of 0.6 at 550 degrees centigrade. Okay. Slowly, he says, with the temperature also it will changes. At room temperature, if you take it as considered as 1, then as the temperature increases, the strength goes down. Okay. Again, steel has a strength ratio of 0.6 at 550 degrees centigrade, for X hours. Again, time. Because again, I have to see based on my load profile whether they need for 10 hours or 2 hours. As I said here, it went to peak. Now I have to match whether it can withstand this or not, this X hours. So I have to cross check all the time. After X hours, the strength ratio goes down because of aging at a temperature load of 550 degrees centigrade. X hours need to be cross checked with the required field hours. As I said, we need to look into the customer load profiles to match the material strength. And okay, now at certain point of time there will be a failure in the useful life. As we said, there will be a constant failure rate. It is not a zero failure rate, but in the useful life also there will be a constant failure rate. But what failure I am targeting really in my product? Did my strength will take care of my failure or not within the specific useful life? So I should know what kind of failure I should target with my strength, because as you can see in the graph, for a product for a certain amount of time, the corrosion starts only at this point of time. But but the requirement of useful life is only this much. So I really need not require a high resistive corrosion material for this kind of application, because it is not even in my target failure at all. It is because the corrosion comes only after my usage life. Bending, if you say bending can happen, probably continuous loading, but it is very marginal. I really need not to worry to take care of my bending. Yes, deformation, yes, I need to really take care of my deformation, and cracks that which can probably come within the material, yes. So we should know what target failures I should look for, and accordingly we need to increase the strength of the product. We should not unnecessarily increase the strength of the material, which will never see that kind of failure at all. So we can put that cost into for certain thing which can improve the useful life. That is very important. You cannot increase the strength for every failure. No. Okay. Even I have every information about the strength. It will work for 550 degrees for so long with this 0.6 strength ratio, everything I have. But still, there will be a point that when this material or component interacts with the other subsystems, then situation will change again. So these interactions also need to be understood and assessed very critically, so that the product will not fail within the useful life. For example, crankshafts, valves within the engine, these are they will interact with so many subsystems. So these are all very critical, even in the engine ECUs, electronic control units. So when compared to the engine, it is little less, but yes, we have certain interactions in the ECUs which I worked, electronic control units. See, generally, if you see electrical components, you see lifetime at temperature 1000 hours at 150 degrees centigrade. Okay. Okay. Now, okay, I know the live data from the supplier. I know the strength of the material. I took everything. Now I said that it will work. It will work for so many hours. So field condition is 85 degrees, and I took the material, appropriate material, which can work 85 degrees for 1000 hours. I can assure you. But now I need to test it. So can I test for 1000 hours and make my customer to sit for 1000 hours? It's impossible. I'm just giving an example. 1000 hours means how many months? You can calculate roughly. Nowadays we need to testing within few hours. Even when you take the mobiles, and the life cycle is 6 months. You will get a new product every 6 months. You cannot wait for 1000 hours. No. Now we will use aging loss, and we increase the test condition to 105 degrees centigrade, and we will reduce the testing hours. So my material should be for 105, not at 85. So reliability engineers should take care even at the stage of testing conditions. My material selection should be according to the testing conditions, not just for the field condition. Very important. So that I can reduce my testing time and so that I can release my product for the customer at the earliest. So when you look at it, the overall product development, we say reliability engineer at the center. He will give the suggestions to the simulation guy, design engineer, testing guys, even to the production. At Bosch, he is the really core for all of these guys. He will, I would say, he will interact with all these stakeholders every time. But he is not the owner of the product for sure. So that is the importance of the reliability engineer in big companies for sure. And very challenging, I am telling you. If any failure happens, they will ask for reliability engineer, did you cross check this, did you cross check that? And very challenging. So with the importance of this, they started a new domain called design for reliability. No, it's not just a design. We should design for reliability. So from the idea stage itself, a reliability engineer will be assigned for that particular product, and he should follow the principles of reliability till the release of the product to the customer. A general step followed in the design for reliability is identify the needs of the customer, convert it into the loads, design them, make sure get a proper design from the designer, analyze them. If you want to use simulations, use them, verify them intermediately, and then finally validate for the required lifetime, and monitor and control. Get the feedback from the customer always. Especially for the infant failures, we need to know why these infant failures are happening. So main advantages: faster time to market, more emphasis on reducing costs, fast moving technology. So when you adopt new technologies which can create new risks into our development programs, you want to design a new valve, new ECU, new UCU casing. So when you adopt any technology which will create new risks, I cannot say risk can be eliminated. We can reduce the risks, and we can identify the relevant risks and then reduce the risks. In this way, reliability is very, very, very important for any industry, at least to my understanding and experience. And during these as we say, whenever we take a new project, so for the development projects using reliability, we really able to put some patents. And I have most of my patents are from Bosch, and one from Siemens, and one from my PhD.